actor-critic methods in deep reinforcement learning. Hey everyone, welcome back. If you've been following along with reinforcement learning, you've probably hit a wall at some point. Policy gradient methods are elegant, but they're noisy. Value-based methods like DQN are stable, but they can't handle continuous action spaces well. So what do? You combine the best of both worlds. Today we're going deep on actor-critic methods, the architecture that powers some of the most capable RL agents ever built, including the ones behind robotic control, game playing, and large-scale simulation. We'll cover why combining an actor and critic works and what problem it solves. A2C and A3C, the foundational algorithms. And a high-level look at PPO and SAC, the modern workhorses you'll actually use in practice. This is aimed at AI students and developers who already have some RL background. If you know what a Markov decision process is and have heard of policy gradients, you're in the right place. Let's get into it. The setup. What are we trying to solve? Before we talk about actor-critic, let's recap the two families it's built from, because the why makes everything else click. Pure policy gradient methods, REINFORCE. In a pure policy gradient method like REINFORCE, we have an agent that directly learns a policy, a probability distribution over actions given a state. We let the agent play out entire episodes, collect the rewards, and then update the policy parameters to make good trajectories more likely. The update rule looks like this. Del theta j of theta equals e of del theta log pi sub theta of a given s times g sub t, where g sub t is the return, the discounted sum of future rewards from time step t. The intuition: if an action led to high cumulative reward, increase its probability. If it led to low reward, decrease it. The problem: high variance. The return g sub t includes all future rewards. It's noisy because it depends on every single thing that happens after the current step, including randomness in the environment. Training is slow and unstable. Pure value-based methods, DQN. On the other side, value-based methods like DQN don't learn a policy directly. They learn a Q function, the expected return for taking action A in state S, QS A equals E, G sub T, S sub T equals S, as sub T equals A. The policy is then derived greedily. Always pick the action with the highest Q value. This is much lower variance, but it has its own limitations. DQN requires a discrete action space. You can't take the argmax over infinitely many continuous actions. And deriving a deterministic policy from a value function means you lose the flexibility of stochastic policies. The actor-critic idea. So here's the core insight of actor-critic. What if instead of using the full noisy return g sub t to evaluate our actions, we use a learned value function to evaluate them? We keep the policy, the actor, but we add a second network, the critic, whose job is to estimate how good a given state or action is. The two components, actor. The policy pi theta of a given s decides what action to take. Critic, the value function VW of S or QW of S, A, evaluates the action taken. The critic gives the actor feedback, not the raw noisy return, but a learned estimate of expected future reward. This dramatically reduces variance, the advantage function. The key quantity in actor-critic is the advantage. A of S, A equals Q of S, a minus V of S. The advantage tells us how much better is this specific action compared to what the agent would get on average from this state. If the advantage is positive, the action was better than expected. Negative means worse than expected. We update the actor to increase the probability of actions with positive advantage and decrease the probability of actions with negative advantage. The update becomes del theta j of theta equals e of del theta log pi sub theta of a given s times a of s, a. This is the core actor-critic update. The noise is gone because instead of a raw return, we're using a learned, smoothed estimate. Practical advantage estimation, TD error. In practice, we don't compute Q of S, and minus V of S directly, because that requires two separate learned functions. Instead, we use the TD error, temporal difference error, as a proxy for the advantage. Delta sub t equals R sub t plus gamma times V sub W of S sub t plus 1 minus V sub W of S sub t. This is the one-step Bellman residual. It says, the value I expected minus the value I bootstrapped from the next step plus actual reward. Positive delta means this transition was better than expected, exactly what advantage captures. Using the TD error as the advantage means we only need to train one critic network, the value function V, not two. A2C and A3C. Now that we understand the actor-critic idea, let's look at the algorithms that made it scale. A3C and A2C, published by DeepMind in 2016. The problem: sample correlation. Before we get to A3C specifically, there's a fundamental problem with training neural networks on RL data: temporal correlation. Sequential experience from a single agent is highly correlated. Each state is similar to the last. Training a neural network on correlated data leads to unstable, slow learning. DQN solved this with experience replay, a buffer of past transitions that you sample randomly from. But experience replay has limitations. It requires storing large amounts of data. It's incompatible with on-policy learning. You need the data to come from your current policy, and it doesn't scale elegantly to recurrent or non-Markovian settings. A3C, asynchronous advantage actor-critic. A3C's solution is elegant. Run many agents in parallel, each in their own copy of the environment. Each agent collects its own trajectories independently, computes its own gradients, and asynchronously pushes those gradient updates to a shared global network. Because each agent is experiencing different parts of the environment at different times, their experiences are naturally decorrelated. No replay buffer needed. The update each worker computes is the standard actor-critic update, using n-step returns for better credit assignment. N-step return: G sub t to the power of n equals ER sub t plus gamma times R sub t plus 1 plus ... plus gamma to the power of n minus 1 times R sub t plus n minus 1 plus gamma to the power of n times V of S sub t plus n. Each worker pushes gradients asynchronously, meaning workers don't wait for each other. This makes A3C fast, but it also introduces stale gradients. By the time worker 5's gradient arrives at the global network has already been updated several times by other workers. This introduces some instability. A2C, synchronous advantage actor-critic. A2C is a simpler synchronous version. Instead of asynchronously pushing gradients, all workers run in parallel and then synchronize. The coordinator waits for all workers to finish their rollout, averages the gradients, and performs a single update. This removes the stale gradient problem, and empirically it turns out that A2C tends to match or beat A3C on most benchmarks, while being easier to implement, debug, and reason about. Key hyperparameters in A2C/A3CA. Few things to know if you're implementing these. N, rollout length. How many steps each worker collects before updating. Longer rollouts give better credit assignment, but slower updates. Entropy bonus. To prevent the policy from collapsing to a single action too early, we add a term beta times h of pi to the loss, encouraging the policy to stay exploratory. This is crucial in practice. Value loss coefficient. The critic and actor losses are combined into a single loss, L equals L underscore policy plus C underscore V times L underscore value minus beta times H of PI. The coefficient C underscore VA balances how much we care about fitting the value function. Modern algorithms. A2C is solid, but it has a practical problem. If you take too large a gradient step, your policy can change drastically. And a drastically different policy might collect completely different, worse data, which then trains an even worse policy. It can spiral. Proximal Policy Optimization (PPO) fixes this. The core idea, trust region PPO, belongs to a family of algorithms that enforce a trust region around the current policy. Don't change the policy so much that it becomes unrecognizable in a single update. The predecessor, TRPO, Trust Region Policy Optimization, enforced this with a hard constraint using KL divergence. Mathematically rigorous, but computationally expensive and hard to implement. PPO approximates the same constraint with a clipped surrogate objective that's dead simple. L clip of theta equals E open bracket min open parenthesis R sub t of theta times A sub t comma, clip open parenthesis R sub t of theta comma 1 minus epsilon comma 1 plus epsilon, close parenthesis times A sub t close parenthesis close bracket, where R sub t of theta is the probability ratio, R sub t of theta equals P sub theta of A sub t given S sub t over P sub theta sub old of a sub t given S sub t. This ratio measures how much the new policy differs from the old policy. If R sub t equals 1, nothing changed. If R sub t equals 2, the new policy is twice as likely to take that action. The clip function limits this ratio to the range 1 minus epsilon, 1 plus epsilon. Typically, epsilon equals 0.2. If the ratio exceeds this range, the gradient from that sample is zeroed out. The amine then ensures we never benefit from stepping outside the clipping region. PPO in practice. PPO collects a batch of experience using the current policy, on policy, then runs multiple epochs of mini-batch gradient descent on that batch. This is more sample efficient than doing just one gradient step per batch. Here's the full training loop at a high level. For each iteration, collect rollout of t steps using pi theta old, compute advantages using GAE, generalized advantage estimation for k epochs, sample mini-batches from rollout, compute, clipped surrogate loss, update. Theta, set theta underscore old, arrow theta, generalized advantage estimation, GAE, is worth noting. It's a technique that interpolates between TD0, one step, low variance but biased, and Monte Carlo, full episode, unbiased but high variance, using a parameter lambda. A sub t to the power of GAE equals the sum of gamma lambda to the power of L times delta sub t plus L, where delta sub t is the TD error. Lambda equals 0 gives you pure one-step TD. Lambda equals 1 gives you Monte Carlo. In practice, lambda equals 0.95 works extremely well. PPO is as close to a default algorithm as RL has right now. It's used in robotics, game playing, and was also used in reinforcement learning from human feedback, RLHF, for training large language models, including some you might have heard of. Modern algorithms, SAC. PPO is great for on-policy settings, but there's a whole class of problems, especially continuous control, where you want to be off-policy. We're using past experience instead of throwing it away after every update. That's where SAC shines. Soft actor-critic, maximum entropy, RLSAC, introduced by Harnoyer et al. In 2018, is built on a beautiful idea. what if we don't just want to maximize reward, but also maximize entropy, the randomness of the policy? The objective becomes J of pi equals the sum over T of E of R of S sub T, A sub T plus alpha times H of pi of S sub T, where H of pi is the Shannon entropy of the policy distribution, and alpha is a temperature parameter controlling the trade-off. Why would we want a more random policy? Several reasons. Exploration. High entropy means the agent tries many things. You don't get stuck in local optima. Robustness. A stochastic policy is harder to exploit and generalizes better to variations in the environment. Multiple optima. In many environments, there are multiple equally good strategies. Maximum entropy RL finds all of them rather than collapsing to one. SAC architecture. SAC is an actor-critic method with the following components. Actor, a stochastic policy pi theta of a given S, typically parameterized as a squashed Gaussian, a neural network that outputs mean and variance, then applies tan H to bound the action. 2 Q networks, critics. SAC uses double Q learning, 2 independent critic networks, Q_W1 and Q_W2. During training, we take the minimum of the 2 Q values to avoid overestimation bias, a known failure mode. Target networks, soft updated copies of both Q networks for stable training. Automatic entropy tuning. The temperature alpha can be automatically tuned so that the policy maintains a target level of entropy. No manual tuning needed. The 3 losses in SAC. Critic loss. L sub Q equals E, Q of S, A minus Y squared, where Y equals R plus gamma times min over I, Q target I of S prime, A tilde prime minus alpha times log pi of A tilde prime given S prime. Actor loss, L sub pi equals E, alpha times log pi of a given S minus min over I Qi of S, A. Temperature loss, L sub alpha equals E, minus alpha times log pi of a given S plus H sub target. If you're training in a fast simulator and can generate experience cheaply, PPO is your friend. If environment steps are expensive, like real-world robot interaction or slow physics simulation, SAC's off-policy nature and high sample efficiency make it the better choice. Putting it together, the big picture. Let's zoom out and see the full family tree. All of today's algorithms descend from the same insight. Combine a learned policy, actor, with a learned value estimator, critic, to get the stability of value-based methods with the expressiveness of policy gradient methods. Policy gradient, reinforce, plus value function, V or Q, leads to advantage actor-critic. A2C/A3C leads to PPO, on-policy, clipped trust region. SAC, off-policy, maximum entropy. If you're looking for where to start, implement A2C on a simple environment like Cartpole or Lunar Lander, then swap in PPO using stable baselines 3. That hands-on experience will make everything we talked about click in a way that no amount of watching videos will. That's it for actor-critic methods. To summarize what we covered, pure policy gradients are high variance. Pure value methods don't generalize to continuous actions. Actor-critic solves both problems. The advantage function is the key signal. It tells the actor how much better an action was compared to the average. A3C parallelizes with async workers. A2C does the same but synchronously and often works better. PPO adds a clipping mechanism to keep policy updates conservative and safe, and it's the most widely used algorithm in practice. SAC introduces maximum entropy RL for continuous control with off-policy learning and superb sample efficiency. If you found this useful, subscribe for more deep dives into RL algorithms. Next up, we're going to look at model-based RL. What happens when the agent doesn't just learn what to do, but also learns a model of the world itself. See you there.